In our everyday lives, the laws of the universe feel comforting, simple, and reliable. These laws govern everything around us, from the flow of water to the motion of objects. Imagine standing by a river. You know the water will flow downhill. If you throw a stone into the air, you can easily predict the trajectory of its fall. Gravity, inertia, and motion are concepts we learn early in school, and they explain much of what we see. Similarly, when you heat a filament in a light bulb, it starts to glow. At first, it emits a dull red light, but as it gets hotter, the light shifts to a brighter orange, then yellow. These changes are predictable and follow the rules of classical physics, a framework that has guided human understanding for centuries. These laws make the universe feel logical, ordered, and accessible. But what happens when we look closer, much closer, into the microscopic building blocks of reality? At this level, the certainty we take for granted disappears, replaced by something almost incomprehensible. Welcome to the world of quantum mechanics, where the rules are not just different, they're bizarre. In this strange realm, particles of matter can exist in two places at once. Their behavior is dictated by probability rather than certainty, and their very existence seems to depend on whether or not they are being observed. Suddenly, the solid foundation of classical physics crumbles. A paradox emerges. For scientists, this was a shocking revelation. They had grown accustomed to a universe that operated predictably, where cause and effect reigned supreme. But at the smallest scales of matter, particles refused to follow these familiar rules. The more they explored, the more they realized that this microscopic world was unlike anything they had ever imagined. As one of the founding fathers of quantum mechanics, Niels Bohr, once said, "Everything we call real is made of things that cannot be regarded as real." In other words, the very fabric of reality, at its most fundamental level, defies our common sense. This discovery marked the beginning of a journey into the unknown, a journey that would challenge the very nature of our understanding of reality itself. The humble beginnings, a problem with the light bulb. At the turn of the 20th century, the light bulb was a symbol of progress, innovation, and modernity. It illuminated homes, powered industries, and revolutionized the way people lived. Yet, this seemingly simple invention posed a question that would baffle scientists for decades. Engineers of the time understood that when an electric current heated a filament, it glowed, producing light. However, the underlying physics of this process was a mystery. Why did the color of the light change as the filament got hotter? Why did it transition from red to orange, yellow, and white, but never to blue or ultraviolet, even at extremely high temperatures? This mystery became known as the Ultraviolet Catastrophe, a dramatic name for an equally dramatic problem. According to the classical physics of the time, as the filament's temperature increased, the intensity of light at higher frequencies, like ultraviolet, should grow infinitely. But in reality, this didn't happen. The filament emitted very little ultraviolet light, no matter how hot it became. This discrepancy wasn't just a minor annoyance for engineers, it was a fundamental challenge to the laws of physics. And it was here, in the pursuit of understanding the behavior of light in a light bulb, that the seeds of quantum mechanics were sown. Max Planck's revolutionary discovery. Enter Max Planck, a brilliant but pragmatic German physicist. In 1900, Planck was tasked with solving the problem of black-body radiation, the emission of light from an idealized object heated to a specific temperature. Planck proposed that energy is not emitted continuously, as classical physics suggested, but in discrete packets called quanta. These quanta were tiny, indivisible units of energy, and their size depended on the frequency of the radiation. At first, Planck saw this idea as a mathematical trick rather than a groundbreaking insight. He himself admitted that the concept was an act of desperation, a last resort to fit the experimental data. But the implications of his discovery were profound. Planck's work solved the problem of black-body radiation, but it raised more questions than it answered. Why was energy quantized? What did these quanta represent? And what did this mean for the nature of light and matter? The scientific community was intrigued but hesitant. Quantization seemed to violate everything they knew about the continuous nature of energy and waves. Yet, experimental evidence was undeniable. Slowly, Planck's radical idea began to gain traction. The concept of quantization didn't just explain blackbody radiation, it challenged the very foundations of physics. If energy could exist in discrete packets, what else in the universe might be quantized? This realization opened the door to a new way of thinking, one that would soon reveal the true nature of light, electrons, and the building blocks of reality itself. But the journey was just beginning. Another phenomenon, equally puzzling, was about to push science even further into the quantum realm, the photoelectric effect. While Max Planck's discovery provided the theoretical framework for quantization, it was Albert Einstein who would take the next critical step. In 1905, Einstein applied the idea of quanta to light itself, explaining a phenomenon that classical physics couldn't, the photoelectric effect. This discovery would not only solidify the concept of quanta, but also earn Einstein the Nobel Prize. The photoelectric effect and Einstein's leap. At the turn of the 20th century, the scientific community was grappling with a phenomenon that defied explanation, the photoelectric effect. It was a simple enough observation. When light struck certain metals, it ejected electrons from the surface. Yet the process behaved in ways that were completely inconsistent with the classical wave theory of light. According to existing theories, light was a continuous wave, and its energy should depend solely on its intensity. A brighter light source, regardless of color, should transfer more energy to the metal, dislodging electrons more effectively. But experiments repeatedly proved otherwise. Red light, no matter how bright, could not knock electrons loose, while even a faint beam of ultraviolet light could do so effortlessly. Moreover, the ejection of electrons occurred instantly, as soon as the ultraviolet light made contact with the metal surface. This was baffling. If light behaved as a continuous wave, the energy should build up over time, like water gradually heating a kettle. But the reality was far different. In 1905, a young Albert Einstein proposed an idea that would revolutionize science. Building on Max Planck's earlier work on quantized energy, Einstein suggested that light was not a continuous wave, but a stream of discrete packets, or particles, which he called quanta. Today, we know them as photons. Each photon carried a specific amount of energy, determined by the frequency of the light. High-frequency light, such as ultraviolet, carried more energy per photon, while low-frequency light, like red light, carried less. This, Einstein argued, was the key to the photoelectric effect. When a photon struck the surface of a metal, it transferred its energy to an electron. If the photon's energy was high enough to overcome the electron's binding energy, the electron would be ejected from the metal. If not, no amount of additional photons or light intensity could dislodge the electron. This was why red light, even at high intensities, failed to knock electrons free, while ultraviolet light, despite its lower intensity, succeeded with ease. The process was instantaneous because it depended on a single collision between a photon and an electron, not on the gradual accumulation of energy. Einstein's explanation was as elegant as it was revolutionary. It resolved the mysteries of the photoelectric effect, but it also challenged long-standing beliefs about the nature of light. For centuries, scientists had debated whether light was a wave or a particle. Experiments with diffraction and interference clearly showed that light behaved like a wave. But now, Einstein's work revealed that light could also behave like a particle. This duality would become one of the defining features of quantum mechanics, reshaping our understanding of the universe. As we delve deeper into this story, we'll explore how these discoveries about light and matter transformed not just science, but our entire understanding of reality. The paradoxes of the quantum world, from wave-particle duality to the nature of measurement and observation, would become the focus of intense debate and groundbreaking research. These ideas would lead to experiments that defied logic, challenged intuition, and ultimately changed the course of human knowledge. Wave-particle duality of matter and light. The idea that light exhibits both wave-like and particle-like properties was revolutionary, but it was only the beginning. What if this strange duality wasn't unique to light? What if the fundamental particles of matter also behaved in ways that defied conventional understanding? This question led to one of the most iconic experiments in the history of physics, an experiment that forever changed our perception of reality, the double-slit experiment. In classical physics, matter and light were thought to be fundamentally different. Matter consisted of particles, tiny and indivisible, like billiard balls. Light, on the other hand, was a wave, spreading out through space like ripples on the surface of a pond. But as scientists delved deeper into the quantum realm, these distinctions began to blur. The double-slit experiment, first performed with light in the early 1800s by Thomas Young, was a cornerstone of wave theory. In this experiment, light passed through two parallel slits and created an interference pattern of alternating bright and dark bands on a screen behind the slits. This pattern could only be explained if light behaved as a wave, with the peaks and troughs of the waves interacting to either reinforce or cancel each other out. When light behaved like this, it was undeniable evidence of its wave-like nature. However, in the 20th century, scientists began to wonder if particles of matter, such as electrons, might produce a similar result. After all, if light could act as both a wave and a particle, why couldn't matter? To test this, researchers adapted the double-slit experiment for electrons, firing them one by one through the slits and onto a detection screen. At first, the results seemed straightforward. Each electron appeared on the screen as a single point, as one might expect from a particle. But as the experiment continued, a strange pattern began to emerge. When enough electrons had been fired through the slits, an interference pattern identical to the one produced by light waves appeared on the screen. This was astonishing. It was as if each individual electron, traveling through the slits one at a time, somehow passed through both slits simultaneously and interfered with itself. This behavior seemed impossible to explain. If electrons were particles, how could they produce an interference pattern? And if they were waves, how could they arrive at the screen as distinct points? The results defied classical logic, forcing physicists to confront the bizarre reality of quantum mechanics. Niels Bohr, one of the pioneers of quantum mechanics, embraced this idea. According to his Copenhagen interpretation, particles like electrons don't have definite properties or locations until they are observed. Instead, they exist as a cloud of probabilities, with the act of measurement collapsing those probabilities into a single reality. This interpretation was both elegant and unsettling, challenging the very nature of what we consider real. Albert Einstein, however, was deeply dissatisfied with this view. He famously asked, "Does the moon cease to exist when I stop looking at it?" For Einstein, the idea that reality depended on observation was unacceptable. He believed there must be hidden variables, underlying factors that determine the behavior of particles, but were simply unknown to scientists. This disagreement between Einstein and Bohr sparked decades of debate, with each defending their interpretation of quantum mechanics. The double-slit experiment and the concept of wave-particle duality have reshaped our understanding of reality. They challenge the classical view of a deterministic universe where everything follows a predictable path. Instead, the quantum world is governed by probabilities, superpositions, and entanglements, where particles can be connected across vast distances and time itself seems malleable. For many, these ideas are unsettling, even disturbing. They force us to confront the limits of human understanding and question the very nature of existence. Yet they are also a source of wonder and inspiration, revealing a universe far more complex and fascinating than we ever imagined. The journey into the quantum realm is far from over. With each experiment, we uncover new layers of mystery, challenging our assumptions and expanding the boundaries of knowledge. As we continue to explore the strange and beautiful world of quantum mechanics, we are reminded of one of the most profound truths of science. The more we learn, the more we realize how much we don't know. Quantum entanglement and Einstein's objections. The quantum world is a place of endless surprises, but few discoveries have been as mind-bending as the phenomenon of quantum entanglement. At its heart, entanglement is a mysterious connection between particles, one that defies all conventional notions of space and time. For Albert Einstein, this was a step too far, a challenge not only to physics but to the very fabric of reality itself. Entanglement arises naturally in quantum mechanics. When two particles interact, their properties can become intertwined, so deeply connected that the state of one particle directly determines the state of the other, no matter how far apart they are. If you measure one particle and find it spinning in a certain direction, the other particle will instantly adopt a complementary spin, even if it's on the other side of the universe. This immediate connection between entangled particles seemed to imply faster-than-light communication, something Einstein famously called spooky action at a distance. In 1935, he collaborated with physicists Boris Podolsky and Nathan Rosen to publish a paper now known as the EPR paradox. In it, they outlined their objections to quantum mechanics, using a thought experiment to highlight the apparent absurdities of entanglement. Imagine two particles are created in a single event and then separated by a vast distance. According to quantum mechanics, measuring one particle instantly determines the state of the other. But how could this happen? How could one particle know what was happening to its twin without any communication? For Einstein and his colleagues, the only logical conclusion was that the particle's properties were predetermined, encoded at the moment of their creation. The EPR paradox sparked intense debate among physicists. Niels Bohr, a staunch defender of quantum mechanics, rejected the idea of hidden variables. He argued that entanglement didn't involve faster-than-light communication or pre-existing properties. Instead, it reflected the fundamental interconnectedness of the quantum world. In Bohr's view, the act of measurement didn't just reveal information about a particle, it actively shaped reality, collapsing the wave function into a definite state. This interpretation, known as the Copenhagen interpretation, was as radical as it was counterintuitive. It suggested that reality itself was not fixed but fluid, dependent on observation. For decades, the debate remained unresolved. Entanglement was a theoretical prediction, something that could be described mathematically, but not tested experimentally. It wasn't until the 1960s that a physicist named John Bell developed a way to settle the question once and for all. Bell's theorem provided a framework for testing whether hidden variables could explain the behavior of entangled particles. His work led to the development of Bell's inequalities, a set of mathematical relationships that any theory relying on hidden variables would have to obey. In the 1970s, physicists began conducting experiments to test Bell's inequalities, using advanced technology to create and measure entangled particles. The results were astonishing. Time and again, the experiments violated Bell's inequalities, proving that hidden variables couldn't account for the behavior of entangled particles. Instead, the results confirmed the predictions of quantum mechanics, showing that entangled particles were indeed connected in a way that transcended space and time. These experiments had profound implications, not just for physics, but for our understanding of reality. They demonstrated that the universe is fundamentally non-local, meaning that events in one place can influence events in another, regardless of the distance between them. This non-locality isn't just a theoretical curiosity, it's a deeply ingrained feature of the quantum world. It challenges our classical intuition, forcing us to reconsider our notions of separateness and causality. For Einstein, the results were bittersweet. He lived to see his ideas about hidden variables discredited, but he never fully accepted the implications of entanglement. Until his death, he remained convinced that there must be a deeper, more intuitive explanation for the strange behavior of the quantum world. In his words, God does not play dice with the universe. But as the evidence mounted, it became clear that the universe was far stranger and far more fascinating than anyone had imagined. Entanglement isn't just a theoretical curiosity, it has real-world applications that are shaping the future of science and technology. Quantum cryptography, for example, uses entangled particles to create unbreakable codes. Because any attempt to intercept or measure the particles would disrupt their entanglement, it's impossible for eavesdroppers to access the information without being detected. This has the potential to revolutionize cybersecurity, providing a level of security that classical encryption methods can't match. Quantum entanglement is also the foundation of quantum computing. a field that promises to transform the way we process information. Unlike classical computers, which use bits to represent data as ones or zeros, quantum computers use qubits, which can exist in superpositions of both states simultaneously. Entangled qubits can perform complex calculations at incredible speeds, solving problems that would take classical computers millions of years to complete. From drug discovery to climate modeling, the potential applications of quantum computing are virtually limitless. But perhaps the most profound implication of entanglement is its challenge to our understanding of reality. In the classical world, objects are distinct and independent, each existing in its own place and time. But in the quantum world, entanglement blurs these boundaries, revealing a universe where everything is interconnected. This isn't just a philosophical abstraction, it's a measurable, testable fact, one that forces us to confront the limits of our intuition and embrace a new, more complex vision of the cosmos. Entanglement also raises intriguing questions about the nature of time and causality. In some interpretations of quantum mechanics, the connections between entangled particles suggest that the future can influence the past, or that time itself may be an emergent property rather than a fundamental feature of reality. These ideas are still the subject of intense debate, but they hint at a deeper, more mysterious layer of the universe, one that we are only beginning to explore. The story of quantum entanglement is a testament to the power of human curiosity. It began as a thought experiment, a challenge to the foundations of physics, and grew into one of the most exciting frontiers of modern science. It has taught us that the universe is not as simple as it seems, that reality is not always intuitive, and that the act of observing the world can change it in ways we are only starting to understand. As we continue to unravel the mysteries of the quantum realm, we are reminded of the words of physicist Richard Feynman. If you think you understand quantum mechanics, you don't understand quantum mechanics. This isn't a statement of despair, but a celebration of the unknown. It's an invitation to keep asking questions, to keep probing the edges of knowledge, and to embrace the wonder of a universe that is far more complex and beautiful than we ever imagined. Quantum superposition and its implications. The concept of quantum superposition stands as one of the most bewildering and fascinating ideas in the realm of quantum mechanics. It challenges the very essence of what we think we know about existence, forcing us to accept a reality where particles can exist in multiple states simultaneously until they are observed. This idea is not just theoretical. It has been experimentally confirmed and has led to technological advancements that are reshaping the modern world. To understand quantum superposition, consider a single electron. In classical physics, the electron is like a tiny marble that occupies a specific position at any given time. But in the quantum world, the electron doesn't have a single definite location. Instead, it exists as a cloud of probabilities, representing all the possible places it could be. This is what physicists refer to as a superposition. Until we measure the electron, it is not in one place or another. It is everywhere it could potentially be, all at once. One of the most famous thought experiments illustrating superposition is Schrödinger's cat, proposed by Austrian physicist Erwin Schrödinger in 1935. Imagine a cat placed inside a sealed box containing a radioactive atom, a Geiger counter, a vial of poison, and a mechanism that releases the poison if the Geiger counter detects radiation. If the atom decays, the poison is released and the cat dies. If the atom does not decay, the cat remains alive. According to quantum mechanics, until we open the box and observe the system, the atom is in a superposition of decayed and undecayed states. This means the cat is simultaneously alive and dead, a chilling, paradoxical state that defies common sense. Schrödinger's cat was not meant to be a literal experiment, but rather a way to highlight the strangeness of quantum mechanics. It posed a profound question. Does reality exist independently, or is it brought into being by observation? In the quantum world, the act of measurement collapses a superposition into a single outcome. Before observation, the system exists in all possible states. After observation, it snaps into one. This seemingly abstract concept has profound implications for how we understand reality. It suggests that the universe at its most fundamental level is not deterministic but probabilistic. The future is not preordained, it unfolds through a series of probabilities that solidify only when observed. For centuries, scientists believed in a clockwork universe where every event followed inevitably from the one before it. Quantum superposition has shattered that view, replacing certainty with possibility. Superposition is not just a philosophical curiosity, it has practical applications that are driving some of the most exciting technological advancements of our time. At the forefront of this revolution is quantum computing, a field that leverages the principles of superposition to achieve computational power far beyond what is possible with classical computers. In a classical computer, information is stored in bits, which can be either 0 or 1. These bits form the foundation of every computation, from the simplest arithmetic to the most complex simulations. Quantum computers, however, use quantum bits or qubits. Unlike classical bits, qubits can exist in superpositions of 0 and 1 simultaneously. This means a single qubit can perform multiple calculations at once. When you combine multiple qubits, the computational possibilities grow exponentially. For example, with just 300 entangled qubits, a quantum computer could represent more states than there are atoms in the observable universe. Quantum superposition is also being explored in the emerging field of quantum sensing, which uses the delicate nature of quantum states to measure physical quantities with extreme precision. Quantum sensors are already being developed to detect gravitational waves, map underground structures, and monitor biological processes at the cellular level. These technologies promise to revolutionize fields ranging from geology to medicine, offering insights that were previously impossible to achieve. While the practical applications of superposition are impressive, the concept itself raises profound questions about the nature of reality. If particles can exist in multiple states at once, what does that say about the universe? Some physicists argue that superposition supports the idea of a multiverse, where every possible outcome of a quantum event exists in a separate, parallel universe. According to this interpretation, when we observe a particle and force it to collapse into a single state, we are not eliminating the other possibilities. Instead, we are choosing one branch of reality, while the other branches continue to exist in parallel. This multiverse interpretation is both thrilling and unsettling. Not everyone agrees with the multiverse interpretation, and the debate over the meaning of superposition is far from settled. Some physicists favor a more minimalist approach, arguing that superposition simply reflects the limits of our knowledge. In this view, the universe is not inherently probabilistic. It only appears that way because we lack the information to predict its behavior with certainty. Others, like proponents of the Copenhagen interpretation, embrace the idea that observation plays a fundamental role in shaping reality. Regardless of which interpretation is correct, the implications of quantum superposition are undeniable. It has forced us to abandon the comforting certainties of classical physics and embrace a world that is far stranger and more complex than we ever imagined. It has given rise to technologies that are transforming our lives and will continue to do so for decades to come. And it has challenged us to rethink our place in the universe, to question what it means to observe, to measure, and to exist. Quantum tunneling and its profound implications. In the macroscopic world, boundaries are solid and immovable. A ball cannot pass through a brick wall, no matter how hard it is thrown, and a car cannot drive through a closed garage door without destroying it. These everyday observations reinforce our understanding of impenetrable barriers, a concept deeply rooted in classical physics. However, the quantum realm defies this logic with a phenomenon so extraordinary that it challenges the very nature of reality: quantum tunneling. Quantum tunneling occurs when a particle passes through a barrier that, according to classical physics, it should not be able to cross. Imagine a ball rolling toward a hill. If the ball doesn't have enough energy to climb over the hill, it will roll back down. That's the classical view. In the quantum world, however, the ball doesn't always behave as expected. Sometimes it simply appears on the other side of the hill, as if it had tunneled through it. To understand why this happens, we must revisit the concept of quantum superposition. In the quantum world, particles such as electrons are not confined to a single location or state. Instead, they exist as a cloud of probabilities, simultaneously occupying many potential positions. When faced with a barrier, the particle's probability wave doesn't abruptly stop at the edge of the barrier. Instead, it extends beyond it. This means there's a small but non-zero chance that the particle can be found on the other side of the barrier, effectively bypassing the obstacle. One of the most significant applications of quantum tunneling is in semiconductors, the building blocks of modern electronics. Transistors, which power everything from smartphones to supercomputers, rely on the precise control of electron flow through barriers. Quantum tunneling enables electrons to pass through these barriers in a controlled manner, allowing transistors to function with incredible efficiency. This phenomenon is the foundation of the microchips that drive the digital age, making quantum tunneling an integral part of the technology that shapes our lives. Another groundbreaking application of quantum tunneling is in nuclear fusion, the process that powers the stars. In the core of the Sun, hydrogen nuclei fuse to form helium, releasing enormous amounts of energy. However, this process faces a significant challenge. The positively charged hydrogen nuclei repel each other due to their electric charge. Classically, they would need immense energy to overcome this repulsion and come close enough to fuse. Yet, in the Sun's relatively moderate conditions, fusion occurs at a rate sufficient to sustain its brilliance. This is possible because of quantum tunneling. The probability waves of the hydrogen nuclei overlap, allowing them to tunnel through the repulsive barrier and achieve fusion. Without quantum tunneling, the stars in the night sky would not shine, and life as we know it would not exist. One of the most fascinating aspects of quantum tunneling is its connection to time. In classical physics, the passage of time is a continuous, linear progression. However, experiments involving quantum tunneling have revealed hints that time may behave differently at the quantum level. For instance, researchers have observed that particles appear to tunnel through barriers almost instantaneously, as if time itself were compressed during the process. This has led some physicists to speculate that quantum tunneling could offer insights into the nature of time, potentially shedding light on some of the deepest mysteries of the cosmos. Quantum tunneling has also inspired bold new theories about the universe's origins. Some physicists propose that the universe itself may have come into existence through a form of quantum tunneling. According to this idea, the universe emerged from a quantum fluctuation in a vacuum, tunneling through an energy barrier into existence. This theory, known as quantum cosmology, suggests that the same principles governing the behavior of subatomic particles might also apply on the grandest scales imaginable. As we delve deeper into the quantum realm, we are confronted with a universe that is far stranger and more wondrous than we ever imagined. Quantum tunneling is not just a scientific phenomenon, it is a glimpse into a reality where the impossible becomes possible, where particles transcend boundaries, and where the mysteries of existence continue to inspire and astonish us. From quantum theory to breakthrough technologies, quantum mechanics has long been a cornerstone of technological advancement, transcending its origins as a theoretical framework to revolutionize industries and reshape human understanding of the physical world. Today, its applications permeate nearly every aspect of modern life, from the devices we use to communicate to the tools that enable cutting-edge scientific discoveries. One of the most significant contributions of quantum mechanics is the laser, a device that manipulates photons with extraordinary precision. Lasers have transformed medicine through advanced surgical techniques, powered telecommunications with fiber optic networks, and revolutionized manufacturing with precision cutting and welding. Similarly, quantum mechanics underpins the development of semiconductors, the foundation of modern electronics. Without the principles of quantum physics, the transistors that drive computers, smartphones, and countless other devices would not exist. Quantum computing is another transformative technology rooted in quantum mechanics. Unlike classical computers, which process information as binary bits, zeros and ones, quantum computers leverage qubits that exist in a superposition of states. This allows them to perform complex calculations exponentially faster than classical systems, opening new frontiers in fields like cryptography, materials science, and drug discovery. Quantum mechanics has also paved the way for advanced imaging technologies like MRI, magnetic resonance imaging, which rely on the quantum behavior of atomic nuclei in magnetic fields to produce detailed images of the human body. These technologies have saved countless lives and continue to push the boundaries of medical science. As we delve deeper into the quantum realm, the possibilities for practical applications only expand. From quantum-enhanced sensors that can detect gravitational waves to advanced quantum networks that promise instantaneous communication across the globe, the influence of quantum mechanics on technology and society is boundless. The practical applications of quantum mechanics have already transformed the world, but its greatest promise lies in the questions it raises. As we explore the quantum realm, we are not just uncovering the secrets of the atom, we are gaining insights into the nature of life, the cosmos, and our place within it. Will quantum physics prove to be the driving force behind the evolution of life? While the answer remains uncertain, one thing is clear: quantum mechanics is a key to unlocking the deepest mysteries of the universe. It is a testament to humanity's boundless curiosity and our relentless quest to understand the world around us. As we look to the future, quantum mechanics will continue to inspire, challenge, and guide us, shaping the technologies, ideas, and philosophies that define the next chapter of human progress. The journey into the quantum world is far from over. It is just beginning. If you look through a powerful telescope at any objects in the universe surrounding you and observe that they are all moving away from you, you might decide that you have a repelling force or that space itself is expanding. Another possibility is that you are at the center of a past explosion and everything is moving away from its center. At first glance, all of these and some other explanations might seem reasonable, but scientists always talk about the expanding universe as if other alternatives are not suitable. One of the most incredible facts associated with Einstein's theory of general relativity is that it relates space-time, matter, and energy. Matter and energy dictate how space-time should curve, and space-time tells matter how to move. If we learn how all matter and energy are distributed in the universe at a certain point in time and how they are moving, we can reconstruct the curvature of space-time and the evolution over the lifetime of the universe. Observing the galaxies in the universe, we see that the gravitational dynamics of neighboring galaxies have the most influence on the closest galaxies to us. For example, the Milky Way and Andromeda are moving towards each other. Other galaxies and local groups will eventually merge as well. The rest of the galaxies are attracted to the nearest masses, large galaxies, galactic groups, and clusters. In any relatively small region of space, ranging from a few million to tens of millions of light-years in size, the mass of this space determines how galaxies will move. However, on larger scales, things don't work the same way. Small-scale movements, known as regular velocities, can reach a few thousand kilometers per second, but they are overshadowed by a stronger effect that can only be seen on larger scales. The farther a galaxy is from us, the faster it is moving away from us. This empirical observation is known as Hubble's law, which postulates that the observed recession velocity of galaxies is proportional to their distance from us. The constant of proportionality in this relationship is known as the Hubble constant. It has been measured quite accurately, and you can see its value on your screen right now. But why does this happen? In reality, why is everything moving away from each other? When Einstein introduced his theory of general relativity, he quickly realized that it had consequences he didn't quite like. A universe uniformly filled with matter would be unstable and prone to gravitational collapse. To counteract this, Einstein introduced a cosmological constant that represented a repulsive force counteracting collapse. Others understood that not accounting for this constant could lead to a non-static universe. In such a universe, the fabric of space would either expand or contract over time. Einstein's correction didn't work, and the cosmological constant led to an unstable universe. Regions with higher density would collapse, while those with lower density would expand. In a universe governed by the laws of general relativity, filled homogeneously and isotropically with matter and radiation, staticity couldn't persist. It had to expand or contract, depending on the content and quantity of the universe. And so, distant galaxies are receding from us faster the farther they are. The reason lies in the fact that a universe that adheres to the principles of relativity, isotropy, and homogeneity, while filled with matter and radiation, cannot be static. It must either expand or contract based on its content and quantity. This situation could have evolved due to various factors. Redshift fatigue. Light coming from distant galaxies loses energy as it travels through space, potentially resulting in a decrease in observed energy and a perceived redshift. High-speed motion. Rapid movement could cause the fastest galaxies to become the most distant over time. Initial explosion. An initial explosive event could push galaxies further away from us. Expansion of spacetime, the last possibility, but the one supported by a comprehensive set of data, including general relativity and the physical distribution and properties of observed galaxies. By the 1930s, it became clear that there were only two options, and the universe is indeed expanding. This was further confirmed by the fact that the redshift of objects correlated well with calculated distance and observed expansion velocity, regardless of the object's distance. But a study from 2011, represented by the red data points, provides the most compelling evidence to date that the temperature of relic radiation was higher in the past. The spectral and temperature properties of distant light confirm the fact that we live in an expanding space. Collectively, all this evidence teaches us that the universe is expanding, and most likely, this is the cause of the redshift. It's not due to motion, tired light, or the result of some explosion. Space itself is expanding. This portion of the universe we can see and study is growing over time. Since the presumed Big Bang, 13.8 billion and 8 billion years have passed, and the majority of objects whose light has reached us are now about 46 billion light-years away. As of now, the observable universe spans about 46 billion light-years in all directions from our vantage point. Beyond these boundaries, there is undoubtedly much more space, likely even infinite. Personally, I'm confident that there is more universe beyond. It's just that light hasn't had enough time to reach us. In this context, whether the universe is finite or infinite doesn't matter. It can still expand. Expanding the universe is like multiplying its size by growth factors. If it was initially finite, it will remain finite but larger in size. If it was infinite, it will stay infinite. The key point is that the universe changes, expands, and stretches. All these effects are consistent and indisputable. What lies beyond the observable universe is a topic for future videos. However, when we talk about distances in the universe, we sometimes find ourselves in a state of shock because our minds can't fathom just how immense those distances are. For example, consider a distance of 10 million light-years. But what if I tell you that the diameter of the universe is about 93 billion light-years from our perspective? The observable universe can roughly be imagined as a sphere with an observer at the center. If you were to observe in any direction, the farthest point you could see would be around 46 billion light-years away. In terms of diameter, this figure adds up to 93 billion light-years. However, if we delve into the age of the universe, this number would be much less than 93 billion. So let's try to understand today how this came to be. To answer this question, let's consider when we say that an object is at a distance of 13 billion light-years from Earth. What do we mean? Is it the current distance to the object, that is, how far it is now when the light from the object started traveling toward us? Or is it the distance that light has traveled? Due to the universe's expansion, these variations should differ significantly. But first, let's use a simple analogy for better visualization. Imagine two adjacent flights of stairs. You stand on one, and your friend stands lower on the other. Your friend tosses a ball to you with a certain speed. It takes some time for the ball to travel to you. If you know the ball's speed and the time it takes, you can calculate the distance to your friend. Suppose the ball travels at 10 meters per second and you are 10 meters away from your friend. Now, let's complicate the scenario. Imagine both of you are on escalators, moving in opposite directions. Your escalator goes up, while your friend's goes down. Each escalator moves at a speed of 2.5 meters per second. Now, things become less straightforward. If your friend throws the ball at 10 meters per second, and you start 10 meters away from them, by the time the ball reaches you, you won't be 10 meters apart anymore. It would take 1 whole second for the ball to reach you, during which you'd move 17 meters away. If you were initially 10 meters apart when the ball was thrown, the moment the ball reaches you means you started at 6 meters away. It took me 0.8 seconds for this scenario. If it took exactly 1 second, it means you started at 8 meters. Now consider that I've rounded the values for simplicity. When two objects are stationary, all three values are the same. For moving objects, they're different. As you know, the universe is expanding, so things get more complicated. When we observe the distant edges of the universe, we're looking into the past. We see light from a time when objects were closer together, and the universe expanded faster in ancient times. Unlike the escalator analogy, the rate of the universe's expansion changes over time. Today, according to modern estimates, the age of our universe is around 13.8 billion years, give or take a few tens of millions of years. What does this mean for distant objects? Let's consider the current record holder, one of the farthest galaxies known to us. When we say it's located at a distance of 13.45 billion light-years, we mean the distance traveled by the light from the galaxy, whether or not it has arrived yet. For me, at least, this seems to be the most reasonable way to measure distances in an expanding universe. In the past, distances between objects were smaller. As light travels from the emitting object to our eyes, the universe continues to expand. But what does this mean for our record holder, this galaxy? Firstly, this galaxy was at a distance of 1.1 billion light-years from us when it emitted the light that has reached us today. Secondly, the light that reaches us today was emitted and sent when the universe was only 380 million years old. Thirdly, the light traveled for 13.4 billion years, and, by definition, covered that exact distance. And fourthly, now this galaxy is located at a distance of 30.3 billion light-years from us. In reality, when you read the news, watch videos, or listen to various scientists, you may not fully grasp the distances they are discussing. So, I've listed all the possible variations. However, usually the last two options are used, either the distance traveled by light or the current distance. Moreover, if the distance in light-years is less than the age of the universe, it refers to the time light traveled. If it's greater, it indicates the current actual distance. The point is, for nearby objects and objects connected by gravity, the difference between these variations is significantly smaller. Nonetheless, I would still prefer people to be more careful with their wording and to use more precise values. If each person specifies whether they mean the distance at the time of light emission, the light's journey, or the current distance to an object, confusion would be greatly reduced. This is how distances work in an expanding universe, and that colossal number, 93 billion light-years, was achieved as follows. The reason is that the accompanying distance to the farthest observable object, namely the surface of the last scattering relic radiation, is about 14 billion parsecs, or 14 megaparsecs. This corresponds to 46 billion light-years in all directions. Thus, the observable universe can be visualized as a sphere with a diameter of about 93 billion light-years, centered on the solar system, the observer's location. Since the presumed Big Bang, 13.8 billion years have passed, at least according to contemporary science. However, this time has passed for us. But since time is relative, what does it mean for observers in other parts of the universe? Does absolute time exist for the entire universe? When we say the universe is 13.8 billion years old, does this only apply to Earth, or does it hold true for the entire cosmos? So, today, let's attempt to understand this. Who knows? Perhaps someone from a neighboring galaxy is looking at us through a telescope right now, observing the dinosaurs on Earth. Furthermore, we will discuss a very unique galaxy that, so to speak, lies beyond our universe. Our Earth exists within the Milky Way, and the ages of everything we see in it match that 13.8 billion years, or almost 13.8. This age of planets, stars, and other sources of light visible in the night sky doesn't align with our own, because as you know, the speed of light is constant. For instance, if you look at a star located 200 light years away, you're seeing it as it appeared 200 years ago. There's nothing paradoxical about this. It's negligible when compared to the 13.8 billion years. Even if we consider a star on the opposite end of a galaxy, at a distance of 100,000 light years, the difference is practically negligible. You might wonder if there's a significant distinction between an age of 13.8 billion years and 13.8 billion 800 million years, or even the specific value of 13,790,900,000 years. I believe the difference is inconsequential. However, if we consider other galaxies that are very distant from us, a completely different story emerges. Each point in this illustration represents a separate galaxy located at approximately 1 billion light-years from Earth. Galaxies within this structure have ages of 12 billion and 8 billion years, while the most remote galaxies are even younger. As we look farther and farther, we find galaxies that existed when the universe was less than 1 billion years old, with its age being only a small percentage of what it is today. With powerful telescopes, you could potentially see individual stars with very low heavy element content. At that time, over 99% of atoms were composed of just hydrogen and helium. Carbon, oxygen, silicon, phosphorus, iron, and other elements necessary for constructing the universe were scarce. This would result in a lack of rocky planets, organic molecules, and the chance for life. When we observe galaxies in their original state, we are essentially peering into the past. Yet, there's a crucial point to note. We aren't seeing galaxies as they are today. Rather, we are observing them from our perspective, looking into the past. For someone on a distant star or in a galaxy tens of light years away, they would see our past. If they were 100 light years away, Earth wouldn't have signs of nuclear bombs. We wouldn't have invented computers, ventured into space, or developed television broadcasts. For someone in a galaxy a billion light-years away, our sun would appear younger and dimmer. Earth would only have single-celled organisms. What's even more astounding is that for observers in the most distant visible galaxies, not only would our Earth and Sun not exist, but our entire galaxy wouldn't either. We'd be a collection of large gas clouds slowly coming together into spiral arms, which would eventually give birth to our home. The oldest globular clusters, currently found in the halo of our galaxy, would also be absent. Nor would there be abundant hot young blue stars, which have vanished a billion years ago. Any of these observers on another star, in another galaxy, or even at the farthest reaches of the universe, would see a universe remarkably similar to ours, an age of 13.8 billion years. A universe where observations peer into the past in all directions, where relic radiation cooled to this temperature, and where the great cosmic web would be indistinguishable from what we see. In this universe, looking at us, they'd see us in the past, just as we see them. But doesn't all of this imply that there's some form of absolute time? Initially, it might seem so, but in reality, it's not the case. If the Big Bang truly occurred, it happened everywhere simultaneously, 13.8 billion years ago. This would be true from the perspective of any galaxy. However, what if there were galaxies moving at speeds not just hundreds or thousands of kilometers per second relative to the coordinate system of relic radiation, but hundreds of thousands of kilometers per second? This speed is very close to the speed of light. Just as time goes differently for anyone moving close to the speed of light on Earth, it doesn't matter if it's a particle, a train, or a person. Though it might seem fantastical, if a planet, star, or galaxy had been moving at speeds near the speed of light for a long time, it would appear significantly younger than the rest of the universe. Imagine that when the universe was only a billion years old, a galaxy accelerated due to a series of gravitational interactions, reaching 99% of the speed of light. Over the 12 and 8 billion years since then, this galaxy would have experienced only 18 billion years. Compared to known galaxies, it would be smaller and less spread out. Therefore, the universe must appear the same to all observers everywhere. The same amount of time should pass, and the universe should possess the same large-scale properties nearly everywhere. However, for some select observers who have spent significant time at speeds near the speed of light relative to the coordinate system of relic radiation, the universe would seem very strange. The moment they slowed down, relic radiation would appear young and the universe old. The fact that 13.8 billion years have passed since the Big Bang would apply to all and everything in the observable universe. You were moving at a speed close to the speed of light. It might be difficult to believe this. However, the conclusions I've shared are based on my perspective living on Earth, in the solar system, and within the Milky Way galaxy. All these conclusions about the age of the universe and various distances are drawn from what I see. To reach these conclusions about the age of the universe, I've studied space on the plate, then what's around me. These studies are based on my perspective. Unfortunately, not everyone is as lucky as me. Not everyone can comprehend that they're part of the universe. Now, let me explain why. For example, in this image, there's a galaxy. The name won't tell you much. You might think it's surrounded by other galaxies, but that's only from a certain perspective. If you were flying through the universe and passed near it, you'd encounter no galaxies there. As far as we know from astronomical observations, this galaxy is in complete isolation. For hundreds of millions of light years in all directions, there's nothing. The bright stars, highlighted by the fractional rays in this image, are actually in our galaxy. This ultra-distant galaxy is much larger and brighter than our Milky Way. It contains 10 times more stars. Behind it lies an even more distant background of galaxies. This background accompanies similar images taken in all directions of the Earth's sky. This galaxy is located in the Pisces constellation. The density of matter in the space surrounding it is about 1 atom per cubic meter. Unlike most galaxies, which are situated along galactic filaments, it's in cosmic voids, empty spaces between them. This galaxy is so isolated that if our Milky Way were in its place, we wouldn't have known about the existence of other galaxies until the 1960s, when powerful telescopes emerged. Now imagine where we'd be if we were at Shocky or the Hooke. The Hooke telescope, used by Edwin Hubble for his research, became operational in 1917. In the 1920s, 30s, 40s, and 50s, we wouldn't have found anything near this galaxy if we lived there. Our searches would have been halted. In that case, we might conclude that our galaxy is the only one in the universe. And indeed, it's amazing that in dark nights, the universe opens up to us. This makes you marvel at how unusual our galaxy's position in the universe is. It also highlights the incorrect assumptions we can make. Having only one point of view can make it hard to understand our true place in this universe. Similarly, a point of view about the birth of the universe can lead us astray, preventing us from truly understanding how everything came into being. Therefore, it's important to consider the universe from different perspectives. In reality, this will be a continuation of this video, and we'll talk about whether it's possible to deceive space and time, and whether it's possible, purely through scientific means, to find oneself between the past and the future, or even in the same moment of time. This illustration represents our cosmic history from the Big Bang to the present day, within the context of an expanding universe. The Big Bang was preceded by a state of cosmic inflation. However, the idea that there had to be a singularity before that is dreadfully outdated. Almost everyone has heard of the Big Bang, but if you were to ask different people, from laymen to cosmologists, to complete the sentence, "In the beginning, there was," you'd receive a multitude of different answers. One of the most common responses is a singularity, which refers to the moment when all the matter and energy of the universe were concentrated into a single point. The temperature, density, and energy would have been infinitely large. This idea could imply the infection of space and time. However, this picture is not just untrue, it's likely been outdated for about 40 years. We are quite confident that there was no singularity associated with the hot Big Bang. Space and time might not have had a moment of origin at all. Let's not rush to make hasty conclusions. Instead, let's explore what we already know on this matter and, most importantly, where this knowledge comes from. Astronomical observations conducted with various telescopes allow us to examine some of the most distant galaxies we have ever seen, many of which are at unreachable distances for us. As we look farther and farther, we discover that the most distant galaxies are moving away from us at an ever-increasing speed, thanks to the expansion of the universe. Today's universe is filled with galaxies in all directions and at various distances. On average, the farther a galaxy is from us, the faster it moves away. This is not due to the galaxies actually moving within their local cosmos. The expansion of space itself is responsible for this phenomenon. This prediction was one of the unusual results derived from the theory of general relativity by Soviet physicist Alexander Friedmann. Edwin Hubble's observations confirmed it. This means that over time, matter in the universe becomes more spread out and less dense as the volume of the universe increases. This also implies that in the past, the universe was denser, hotter, and more uniform. Extrapolating backward in time, we arrive at early, hotter, denser states. But does all of this lead to singularities where the laws of physics break down? When you extrapolate the universe's development backward in time, you start to notice several important changes. In particular, you'll reach an era where gravity didn't have enough time to form sufficiently large clumps of matter for stars and galaxies to form. Then, you'll arrive at a point where the universe was so hot that it couldn't even form neutral atoms. Beyond that, there will be a state where atomic nuclei themselves break apart. Then, you'll witness the spontaneous appearance of pairs of matter and antimatter particles, and then you'll see where individual protons and neutrons will decay into quarks and gluons. The thing is, regular physics, including the moment of the universe's beginning, breaks down in a singularity. However, achieving an infinitely hot and dense state has its consequences, many of which, unfortunately, are not confirmed by observations. Each step represents a universe that's progressively younger, smaller, denser, and hotter. Continuing this extrapolation, we see that the densities and temperatures increase to infinite values at the moment when all the matter and energy of the universe were contained in a single point, a singularity. However, the hot Big Bang, as initially thought, wasn't just a hot, dense, and expanding state. The moment when all the laws of physics ceased to work was the birth of space and time. It's a way to suddenly make the entire universe appear out of nothing. It was the original act of creation. The singularity is associated with the Big Bang, but if everything happened as described, and the universe in the past had infinitely high temperatures, there would be certain obvious signs observable even today. However, for now, let me remind you what fluctuations are. Fluctuations are oscillations, meaning any random deviation from a certain value. In the context of the Big Bang, there would be temperature fluctuations of enormous amplitudes, temperature fluctuations that would be limited by the speed of light. They would only occur on scales not larger than the cosmic horizon. Relics of high-energy cosmic materials, such as magnetic monopoles, should have remained, but temperature fluctuations don't exceed 1 part in 1,000, which is 1,000 times smaller than what the singularity-based Big Bang predicts. Fluctuations larger than the horizon have been confirmed by various satellites, but the constraints on the existence of magnetic monopoles and other relics of ultra-high energy are extremely strong. The absence of their presence has serious consequences. The universe never reached extremely high temperatures, so there must be some boundary. We can't extrapolate back infinitely far to a hot, dense state with infinitely high temperature. Moreover, there's a limitation on how far we can go while accurately describing our universe. In the early 1980s, a theory emerged that before our universe was a hot, dense, expanding, cooling, matter and radiation-filled state, it underwent a phase of inflation. The presence of a cosmic inflation phase should have meant that the universe was filled with energy inherent to space, leading to rapid expansion that stretched the universe into a flat state with uniform properties everywhere. This would have involved small amplitude quantum fluctuations at all scales. Inflation causes space to expand exponentially, which can rapidly cause initially curved or uneven space to appear flat. And even if the universe were curved, its curvature radius would be at least hundreds of times larger than what we could detect. When inflation ends, it converts the energy inherent in space itself into matter and radiation, giving rise to the hot Big Bang. However, this doesn't lead to an infinitely hot Big Bang, only one that reaches a maximum temperature hundreds of times lower than what's needed for a singularity. In other words, it leads to a hot Big Bang emerging from an inflationary state, not a singularity. The information existing in our observable part of the universe that we can measure only corresponds to the last few seconds of inflation and everything that happened after that. If you were to ask how long inflation lasted, you wouldn't naturally find an answer to that. It continued for at least a little longer than those seconds, but whether it continued a bit longer than that, significantly longer, or for an infinite amount of time, that is not just unknown, it's fundamentally impossible to know. But then, what did inflation give rise to? Many studies and discussions revolve around this topic, yet no one knows the answer because there's no evidence to rely on. There were no observations that could have been straightforwardly made. Consequently, some individuals or scientists make mistaken claims. For instance, one of the claims was that we had a theory of singularity-based Big Bang, which generated a hot, dense, expanding universe before we learned about inflation. Inflation is actually an intermediate stage, so we get the following sequence: singularity, inflation, hot Big Bang. There are numerous graphs and images created by leading cosmologists that illustrate these data, but it doesn't mean they are all accurate. They illustrate density fluctuations and gravitational waves arising after inflation. The assumption of a singularity before inflation doesn't necessarily hold. There's a very strong basis to believe that it's not the case. Mathematically, we can demonstrate the impossibility of transitioning from a singularity to an inflationary state. And that's why the space-time of inflation expands exponentially. Imagine how an exponential function works. After a certain amount of time passes, the universe doubles in size. After twice that time, it doubles again, which means it becomes 4 times larger. Wait for 3 such intervals of time, and it triples. Wait for 10 or 100 such time segments, and these doublings will make the universe 2 to the power of 10, or 2 to the power of 100 times larger. This means that if we go back in time for the same duration, or for 2, 3, 10, or 100 times longer, the universe will become smaller and smaller, but it will never reach zero. It will always be a fraction of its initial size, such as half, a quarter, an eighth, 2 to the power of -1/10, or 2 to the power of -100. No matter how far back in time we go, we'll never arrive at a singularity. The blue and red lines represent the traditional scenario of the Big Bang, where everything begins at time t equals 0, including space-time. In the inflationary scenario, represented by the yellow color, we never reach a singularity where space takes on a singular state. It could become arbitrarily small in the past, while time continues infinitely. Among cosmologists, it's well known that there's a theorem demonstrating the incompleteness of the past inflationary state. This means that all particles existing in the universe undergoing inflation will eventually meet when extrapolated backward in time. However, this doesn't imply that the singularity necessarily existed. Inflation simply doesn't describe everything that happened in the history of the universe, including its birth. It is also known that inflation cannot arise from a singular state, as the region undergoing inflation must always start with a finite size of space-time fluctuations on a quantum scale during inflation, which stretch across the entire universe and give rise to imperfections in density and gravitational waves. However, whether inflation emerged from a singularity or not is unknown. So every time you see a diagram, article, or history about the singularity of the Big Bang that existed before inflation, know that you're dealing with outdated scientific facts. The idea of the singularity of the Big Bang lost its relevance as soon as we understood that there was another state before the hot and dense state of the Big Bang, cosmic inflation, which likely prepared and initiated the Big Bang itself at the very beginning of space and time. Possibly, a singularity from which inflation emerged existed, but there is no guarantee. In science, there are things that can be checked, measured, predicted, confirmed, or refuted. For instance, inflation giving rise to the hot Big Bang is substantiated. Everything else is merely idle speculation. Therefore, To understand how our universe was born, it's worth considering all possible scenarios of events. If you ask any scientist if the universe has a boundary, you will likely receive an ambiguous answer, because on one hand, the universe has an end from our perspective, particularly in terms of observations. This is known as the observable universe. But if we look at science from a different angle, we understand that our universe is expanding with acceleration, thus there cannot be any limitations. You will get approximately this answer, but only with detailed arguments, formulas, and explanations of why everything is the way it is in this world. It's known that due to the expansion of the universe, there exists an event horizon beyond which we cannot penetrate. We are witnesses to the fact that there is at least one intelligent life form. Believing whether we are alone or if there is someone else out there is a personal matter for each individual. However, let's imagine that in a distant galaxy there is another civilization, and naturally the event horizon for them is of the same size. And from their point of view, they could observe those parts of the universe that are beyond our horizon. Roughly speaking, they know what is unknown to us. Let's assume that an interesting cosmic phenomenon or a unique galaxy they observed astounded them so much that they wanted to tell us about it. With the help of some mega-advanced and unique future technologies, we receive their signal with this information. In that case, we would learn what lies beyond our event horizon. What do you think? Is this theoretically possible without violating the modern and known laws of physics up to 2019? So let's delve into all this in more detail. On one hand, we can trace the universe's history back to its very beginning, to the Big Bang 12 and 8 billion years ago. We have this magnificent image of the universe captured using background radiation. We can also observe stars and galaxies that formed during that time within the reach of modern telescopes. At the moment, the record is held by light that traveled to us for 13.7 billion years from an object currently 33 billion light-years away. Only the most advanced telescope could surpass this record. But the essence is that our observations are limited to the observable part of the universe since the moment of the Big Bang. Light traveled 13.8 billion years, meaning we can only see the light that traveled that many years in any direction. However, this doesn't mean there's no universe beyond this border. We're sure it's there. After all, light still reaches us, and the question is about how much of it is there. And here, our experiment begins. If there's a limitation on what can be seen, then this limitation also applies to those observers whose light is visible differently. In other words, if we take two galaxies situated on opposite sides of us, and the light from them traveled 13.7 billion years, we can see both of them, but they won't see each other. If each of them has intelligent beings, couldn't they send us information about what they see, which is unavailable to us? Could they thus deceive the limitations of space-time and provide us with information about the part of the universe we can't see? Or could we send them images of the faraway galaxies captured by the Hubble extreme, or even a map of the universe as we see it? If we continue exchanging this information, would each participant eventually know more than they can see with their own eyes? However, there's a catch. Let's remember light from a very distant object. The thing is, that light would be old. If we see something whose light traveled to us for 12.4 billion years, and the object is now 33 billion light-years away, we see it as it was 400 million years after its creation. Of course, it's a distant galaxy and is still emitting light, but we'll never receive it. The universe isn't just expanding, the expansion is accelerating, and this is a firmly observed fact. The question is why it's accelerating. The biggest explanation for this is dark energy. We'll talk about that later, at least explaining what's generally understood as dark energy. So the light emitted by galaxies beyond certain limits will never reach us. If it weren't for dark energy, we would eventually see it and receive the information they sent, but only after the light emitted by those galaxies reached us. Therefore, we can get information from objects beyond our horizon, but only after they move inside our horizon. And due to dark energy, whatever gets inside our horizon is already gone. This viewpoint is examined from one perspective, taking into account the theory of the Big Bang as the beginning of the universe, and nothing prevents us from discussing it in a few episodes.